with the switch closed, what logic level is going in? 1. What is coming out? 0 volts or 0? Same thing.
Why are we getting 0 volts now?
Because I'm grounding that point.
This is in reference
That
to
makes sense
VL.
now.
Yeah, it's always referenced to V out. Everybody all right with that?
Mm-hmm.
Okay. So 1 in, 0 out. What have I made?
Not switch.
I've made a NOT gate, an inverting gate. This is a NOT gate. Now I have to pay somebody to flip that switch. And a mechanical switch is big and ugly and takes too much room, all right? So we can't do that. What would happen, do switches have resistance associated with them?
Infinite and 0.
One would use the light. Do you suppose a switch really has absolutely 0 resistance? Not unless you've got it cryogenically cooled or something down to 3 degrees Kelvin. Okay, there's resistance associated with it. So if I told you that the switch had 4 milliohms worth of resistance, has anything altered? What are you getting out in this case here? 4 milliohms. What are you getting out?
Would it not still be 1?
No. The switch is closed. The switch is closed. And it has a 4 milliohm resistance. Of course it's not very significant. Yes? You have analyzed circuits like this multiple times in lots of courses. Isn't that the effective circuit for the thing? Okay. So what voltage is coming out? 0, essentially, right? Voltage divider is 4 milliohms over 1K plus 4 milliohms. 0, right? Okay. What happens when the switch is opened? What do you get out?
5 volts.
5 volts. Okay. Now, what happens if the switch has a resistance of a kiloohm? Good or bad? Bad, because when the switch is now closed, what are you going to get out? 2.5 volts. Is that very good for a logic system? No. Okay, what would happen if the switch had 400 ohms?
Still not very good.
Still not very good. Okay. What would happen if instead of making that 1K, I made it 10K? Would a 400 ohm switch resistance hurt me much?
Not as much.
Not as much. Okay. Now, looking at this thing here, in this state here, how much power is consumed by my gate? Here's my gate. How much power is consumed?
None. There's no current.
There's no current. When I put in a logic level 1 and trying to get a 0 out, is there any power being consumed by the gate? Okay, I'm putting in a logic level 1. How much power is the gate consuming?
4 milliohms times 25 volts.
circle is the gate? The whole package. Is there current flowing? Yes or no? You said no? Don't own up to it. Of course there's current flow. How much power is being supplied by the 5-volt source to the gate? How much current's flowing?
5 milliamps.
5 milliamps. Yes? So how much power are we consuming?
25 times.
5-1.
I hope not 5 volts. Put enough of these in and we can heat the room.
Be 25,000. Take that back, I take that back.
25
There we go.
milliwatts.
I went the opposite.
25 milliwatts would be the power consumed. Does that sound like a lot?
Yeah, but it's enough.
It's relative here, okay? If you were talking about, you know, that switch over there dissipating, 25 milliwatts, insignificant compared to the other power here. But if you're talking about having a million of these things together to make up a computer, each one consuming 25 milliwatts, is that significant? The answer is absolutely. What could I do to improve the situation and would not affect the functioning of this thing very much?
Smaller voltage range, like 0 to 3.
Okay, smaller voltage range would do it, but I'm stuck with 5 volts for right now.
Decrease your resistors.
Pardon?
Decrease your resistors. Or increase.
We want the resistors to go up or down. Up. You want larger resistor values. So if I made this a 10K, now what? How much current would be flowing? 0.1 milliamp, right? Okay. And so you see that the power is going to be significantly less. So why not make that really, really large? Let me make that to be a mega ohm or something. We'd really have low power at that point, correct? The only downside with doing this is that when you drive another gate, we're going to see that most gates have some type of input capacitance. And so if you start jacking up the resistor too high, what happens to the rise time of our signal or the fall time? Remember, we were talking about blowing up the balloon over there? So you start jacking up that resistor value and now what? It slows the gate down. Can't stress this enough. Anytime in design, you try to fix one parameter, you're squeezing it, something pops out someplace else. Okay, so design is always about trade-offs. Doing okay? All right, so having a switch there, while it sounds good, it's not very good. We don't want mechanical switches there. So we want an electrical switch. So let's make this is an MOS transistor, and I'm gonna not, you went through probably BJTs in 245, yes? All right, so I'm gonna go over CMOS or MOS transistors right now. So, well, let's start at the very beginning here. How do you make a diode?
2 different materials.
2 different materials. So what we're going to do is we're going to take pure silicon here, and you know that silicon is covalently bonded with its neighbors. It's got valence of 4 electrons. and it's a covalent bonding, and they like to share with the other guys, right? So is pure silicon a conductor, dielectric, or insulator?
Insulator.
Okay, it's not a pure insulator. It's not a very good conductor either. It's, you know, it's kind of in between there. Well, if I add impurities, and you talked about this, we could add boron or phosphorus, and so we could add a +3 valence atom in there, and it's only going to have 3 electrons that it could share. Well, the silicon neighbors have 4 each. So there's an extra electron kind of floating around. So this would be an N type of material here. It's electrically neutral, but if you look at it and if you apply a voltage across it, electrons want to flow through those impurities. Now the number of impurities are down in the parts per billion. I mean, it's not like we're dumping a whole lot of impurity into this thing. Okay, we could also add a +5 impurity, and this is going to make a P type of material. And here, the extra atom is going to have an extra proton or positive charge that wants to flow around. Again, whole section is completely electrically neutral because there's always the same number of electrons and protons in there. But it would look like we applied a field across it that a positive charge was moving. Doing all right? So this is the N, this is a P. It looks like electrons want to flow. This guy looks like positive charges want to flow. So if I were to do this here, put a battery like that, I'll put a dropping resistor. Which way does current want to flow? This is good old Ben Franklin current. Current wants to go which way? That way. That means that electrons want to go where?
The opposite way.
The opposite, okay. So these electrons here, man, they really want to come up here. Why? Because they want to get to this positive side of the battery, right? Well, what about the positive charges? They want to go which way?
The opposite direction.
They would really like to stack up here trying to get to this guy. What does that give you in the middle? Nothing. So how much current flows?
None.
Okay. So my orientation for this is like that. You've seen that diode symbol there? Yes? Okay. Can current go through that direction? The answer is no. Not in this orientation. Is that all right? Okay. Now, which side is the anode and which is the cathode?
Anode is the top one and cathode's the bottom.
You're saying this one's the anode and this one's the cathode?
Yes.
Why?
When I think
Is that
anode, I
the
think
charge
negative
side?
charges.
What is an anion?
It's got a negatively charged.
Okay. And what's a cation?
The opposite.
Great. So what's an anode?
Negatively charged.
No,
You can thank chemists for screwing you up here. The anode of a battery is the positive terminal because anions are attracted to it. Yes? So, which is the anode and which is the cathode of this diode? The opposite.
tricky.
Yes, it is.
Wait, can you make your statement again about the cathode is where?
Cathode attracts cations. The anode attracts anions. Okay. So anode is the positive end of the battery, cathode is the negative. All right, so nothing exciting is going to happen here, but I flop it, and then what?
Charge wants to flow.
Now I'll get current flowing, correct? How much current flows? Infinite amount, right? Wrong. How much flows?
How much is necessary?
Ah, very good. So if you put your diode curve like this, and typically for a silicon diode, the turn-on voltage is about what?
0.7.
0.7, very good. You superimpose on that the circuit looking out that way there. This is -1 over the resistor value for the slope of that line if this is current and this is voltage here. What's the maximum voltage looking across the diode there? What's the maximum voltage we could ever see? It would be our VCC.
So, in the left diagram, current wouldn't flow. but-
It would not.
Okay, so in the right diagram, when we
It would
correct
not.
So this side wouldn't flow either?
No, because this is the symbol
Right.
for the diode. If I want current to flow, I've got to flop the diode around.
Oh, okay, so you're saying, so the right is a representation of the left, and both of them will not have current flow?
That is correct. So you find out where the thing operates by superimposing the VI curve of the diode and the VI curve of the load, and this guy here is the load. You superimpose that and you'll find out where it's going to operate at. Did you do stuff like that? You should have. All right. Okay, so if to make a diode, we did an N and a P material, right? So how about if I do this? An N and a P and an N material. And once again, I put my battery across it like that. What's going to happen?
It would flow neither way, either way.
I don't know about the grammar, but you're exactly correct. Nothing is going to happen. What you've made is a really expensive open circuit. Why? Can you see that this looks, if I split that P material in half, that looks like two diodes back to back, yes? One of them's going to be open. One would like to let the current flow, the other one says no, 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 no. What about this one here? Would it like, for this circuit, would it like to let the current go?
Yes.
Yes. But that one is going to be reverse biased, and it says no, it can't flow. Well, what would happen if I did PNP?
The opposite.
But nothing exciting is going to happen. Well, what I can do though, now this is not the way that the transistors are made. A BJT transistor is really made like this. So here is my N, my P, and my N. Okay, so this guy is the collector, the emitter, and the base. If I inject a very tiny amount of current in there, that will cause a large current to flow between the collector and the emitter. Is that all right with everyone? You should have seen this back in your 245 days. That the BJT transistor is really a current amplifier. So if I don't have any current flowing, what's going to happen? The device is no current flowing. What's going to happen? Meaning no current's going to flow here, right? We're back to this guy here. But if I inject a small amount of current in here, then I can open that thing up. Okay. And the BJT transistor, when you put a lot and a lot and a lot of current in there, it goes to a voltage of about 0.3 volts. Okay, it's saturated.